Structural patterns are all about how classes and objects are composed to form larger structures. If a certain city had design patterns, for example, these would be the ones deciding how to build houses, how they connect, and how you expand them without breaking the whole neighborhood. Hello everyone, and welcome to one more episode of the Tech Odyssey podcast. I am your host, Mike, and together we explore the world of tech and everything around it. Today, we are going to dive into something that every developer hears about, but not every developer truly understands: structural design patterns. They are the patterns that help us structure our code, make systems easy to extend, and keep everything from turning into a giant plate of spaghetti. Before we dive into each pattern, let's set the foundation. Structural patterns are all about how classes and objects are composed to form larger structures. If a certain city had design patterns, for example, these would be the ones deciding how to build houses, how they connect, and how you expand them without breaking the whole neighborhood. In software, structural design patterns help you with reusing existing code, adapting incompatible interfaces, improving flexibility, reducing coupling, adding features without rewriting everything. We're basically talking about smart architecture. So let's start going through our patterns one by one. Let's start with the first one, the adapter pattern. The adapter pattern basically makes things compatible. Imagine you buy a device with a US plug, but you live in Europe. So what do you need? An adapter. In code, we use the adapter pattern to make two incompatible classes work together without modifying them. You create a new class called the adapter. This class implements the interface that your code extends. Inside, it translates the call to the method of the class that you are adapting, and therefore you don't have to modify the existing class. The adapter just sits in between. When you use it when you are integrating an API into existing code, you are working with legacy systems, or when you are converting data formats. Let's go to the next one on the list, the facade pattern. The facade pattern basically is simplifying a complex system. It gives you a single interface to something that is complicated underneath. It's like ordering coffee. You don't need to know how the machine works internally. You just tap the button and the coffee is made. You create a facade class with a clean, simple set of methods. Inside those methods, the facade calls multiple complex subsystems, and clients only use the facade, not the clutter that is underneath. You will probably use it when you are exposing a clean API or when you are creating an SDK, when you want to hide internal complexity, or where you are organizing messy code bases. Next up is the composite pattern. Think of a folder inside your computer. It might contain files or other folders, but you can click delete on both files and folders. They behave similarly, even though they are different. Composite lets you treat individual objects and groups of objects in the same way. You create a common interface, let's say a component, then you create leaf classes and composite classes. The leaf classes are for single items, while the composite classes are for groups of items. The composite contains a list of components, meaning that it will hold both leaves and also other composites. And then every operation is delegated to the children, which allows recursive structures. You will use it when you have tree structures like menus, UIs, or file systems, when you are building nested hierarchies, or when you have operations that apply to both single items and groups. Next up is the decorator pattern. The decorator basically adds features without changing code. Picture a coffee again, plain espresso. Then you add milk, then you add sugar, then you add caramel. Each topping decorates the original coffee. Decorator lets you add behavior to the object dynamically without modifying the class. When you use it, when you have logging, caching, authentication, or when you have to add behavior in runtime. And then we have the proxy pattern. Proxy pattern controls access to something. A proxy stands between you and another object, basically. It's like a bodyguard deciding who gets into the club. The real object might be expensive to create, or it's remote, or it might need protection. The proxy manages the access. In the code, you need a proxy class that implements the same interface as the real object. The proxy holds a reference to the real object. Method calls go through the proxy first, which can check the permissions, do lazy load of the object, cache results, and do remote communication logic. After that, it forwards the call to the real object. You will use it for lazy loading, for security and access control, for remote communication like RPCs, caching, or rate limiting. And then you have the flyweight pattern. Flyweight pattern is meant to reduce memory by sharing objects. If every snowflake or tree in a video game were a separate object, your GPU would explode. Flyweight solves this exact problem by sharing common data between many objects. In the code, you separate data into intrinsic state, which is shared and never changes, and extrinsic state, which is passed from the outside. You store and reuse shared objects in a flyweight factory, and when code requests an object, the factory returns an existing one instead of creating a new one. You will probably see this in games where you have to create trees, particles, or bullets, in UI elements, or anything with a huge number of similar objects. Finally, you have the bridge pattern. The bridge pattern is meant to separate abstraction from implementation. It basically says, let's split the what from the how. It splits the abstraction from the implementation so they can actually evolve independently. The abstraction defines what something does. The implementation defines how it does it. And you can mix it up and match them. In the code, you define an abstraction class with high-level methods. You define an implementation interface that contains low-level operations. The abstraction holds a reference to the implementer and delegates work to it. And now you can mix up and match different abstractions with different implementations. When you use it when you want to avoid class explosion, in multi-platform applications, in GUI tools, device drivers, or different rendering engines. So why should you care about structural patterns in the first place? Because structural patterns help you build modular systems, keep logic clean, make code testable, and adapt to change and extend features without rewriting everything. Also, it helps you think in terms of architecture rather than just ad hoc fixes. And honestly, understanding these patterns just makes you a better engineer. So that was our tour on the structured design patterns for today, the building blocks of flexible software design. If you enjoyed this episode, subscribe and share it with a friend that might find it useful. In the upcoming episodes, we are also going to see behavioral patterns, real-world examples, and how these patterns appear in systems that you use every day. Thanks for joining me in one more episode of the Tech Odyssey podcast. I am Mike, and I will see you in the next one where we'll keep exploring the world of tech one step at a time.